Right. So we'll just take a minute more and then we'll start.
Yeah, sounds great.
Right. It's time to start. So hello, everyone. Welcome to our second QWebinar during our summer school. And today we are very pleased to have Nathan Wiebe from University of Toronto. Before we begin, just like yesterday, please remember our protocol, I guess. We want to make sure everyone has a nice and safe environment for discussing. Let's ensure that. If you do want to record, we request that please don't record this session. We will be recording the video and we'll make them available to all the participants. So I guess that makes it easy for everyone. And if you have questions, you can communicate either via the Zoom chat window or via YouTube comments. But rather than asking them right away necessarily, I'll collect them towards for the end of the talk. Unless there's a question that seems very relevant to kind of interrupt Nathan right in the middle and then ask right then and there. Otherwise, we'll collect the questions for the end of the talk and then kind of just do all of them together at the end. With that, let me introduce Nathan, who's our speaker for today. So Nathan is a professor at University of Toronto, and he did his PhD at University of Calgary, and we were there together for a while as well, so it's great to see him again. After that, he did his postdoctoral work at University of Waterloo and spent time at Microsoft as well, and I think at the University of Washington and Pacific Northwest National Laboratory before ending up in Toronto, right? So he's been kind of around, and he is really known very well for his pioneering work in quantum simulation, quantum machine learning. There's lots of recent articles that have been wonderful to read from him. So it's great that we have a chance today to hear from him directly. So with that said, let me welcome Nathan, and he can start sharing his slides and take it from here.
Wonderful. Thanks a lot for the intro, Gibran.
Okay.
Let me share my screen. All right. Gibran, are the slides showing up okay?
Yes, it's fine.
Wonderful. All right. Well, thank you very much, everybody, for coming. I'm really excited to get the opportunity to talk to you about quantum machine learning. And one of the things I wanted to be kind of a little bit more clear about is in part my current thought process about why I do quantum machine learning. And in part, that's actually given in the title here. What I'm mostly interested in is, I mean, when people approach quantum machine learning, there's a couple of reasons why they end up approaching it. In part, one of the big reasons is that, well, machine learning is big these days. Most major firms have at least some investment in machine learning. Some, essentially, they're just machine learning companies like Google, for example, and Microsoft. All of these companies have major investments inside in machine learning, and it pervades just about all of their products. And so, especially with the end of Moore's law and everybody looking for new computational platforms that can help us provide more computational power to meet the ever-increasing demand for compute from ML and other applications, people have begun to increasingly turn their attention to quantum computing as being something that could potentially revolutionize machine learning. And this is one of the big motivations that people end up having for looking at machine learning, although in a quantum world. But in my case, actually, I'm less interested in this. The thing that makes me fascinated about machine learning really is a different question. And that question is, well, what does it even mean to learn for quantum systems? how can we think about quantum learning agents? Because my firm belief is only once we understand really what learning actually ends up meaning in a quantum environment, can we start seeing the genuine fruits of quantum algorithms for solving problems in machine learning. So the main purpose in this talk is to give you some idea about the current thought processes that people use in order to try to apply quantum technologies to solve problems within the ML space, as well as some of the ways that I like thinking about machine learning problems in general that kind of map them to a quantum friendly way, or more accurately, kind of allow us to begin thinking about learning directly from quantum data. And I'll discuss in more detail about what exactly I mean by that later on in the talk. But yeah, those are the kind of the main points that I really want to get across. Now, the field has grown like mad since its inception. And if you want kind of a more comprehensive list of some of the things that are impacted, or the techniques that we have for solving this, I recommend you take a look at my review article with a bunch of other co-authors that's published in Nature. But even that's starting to get a little dated because the field is moving so quickly. So I want to present some of those ideas as well at a rough level, and then finally spend some time talking about newer ideas about how we can end up getting around issues facing gradient descent for quantum models. So just to give you an idea about like what machine learning tasks end up looking like, for those of you who haven't done too much ML in the past, the basic idea behind ML is that what we really want to do is really want to be able to get a computer to perform a particular task. The problem is that for many problems that ML is a good solution for, we actually don't have a great way of being able to explicitly tell the machine what the particular task, or how we really want it to optimally solve that problem. So instead, usually what we'll do in machine learning is we'll come up with a model that will a parameterized family of models. And then what we'll do is we'll feed in training data in order to be able to find the parameters for those models that end up performing best on the task. So perhaps visually the most straightforward model for machine learning is the support vector machine, or linear perceptron. As you can see on the left. And this task over here that we would be using it for would be to classify points. So here I've shown a data set consisting of red points and blue points. And the problem that we would like to solve using this is we'd like to be able to figure out, if we were given a point and weren't told its color, do we think is it a blue point or is it a red point? Well, we can see immediately just by looking at this data, right, how we could come up with a good rule for deciding whether a point is red or blue. You can see that if we, this line that's been helpfully drawn in the plot, all the red points happen to be above the line and all the blue points happen to be below the line. So that's all we would have to do. If we knew where that line was, we could figure out whether a point should be classified as red or blue by seeing which half space that point ends up lying in. And so this is basically the simplest machine learning, one of the simplest machine learning algorithms you can think of. And in order for us to be able to train it, what we do is we would give it a bunch of these red and blue points, and we would rotate this line in such a way as to maximize the accuracy. And technically, if it's a support vector machine, to also at the same simultaneously maximize the margin between the line and the two classes of red and blue points. But once you have that, then you can use the model for taking a look at everything. Again, with everything in machine learning, the quality of the model that you end up getting out depends on the quality of the points that you end up putting, or training data that you put in. And so if you provide a lot and good data, then the models can actually be quite performative that end up coming out. However, if you pick bad data, then the models can be quite poor. And there's some wonderful stories that you can find in the literature about what happens when you give a reasonable model horrible data, and it'll find some amazing correlations sometimes that you did not intend it to find. But in any case, that's the idea. Now, you can see, you might ask, okay, well, for a data set this simple, right? Why am I even bothering to use a computer? I could just stare at this. But the thing is that partially the reason why you can stare at this and figure out what a good separating line is between the classes ends up coming about because of the fact that this is just a two-dimensional problem. Because it's 2D, you can visualize it. But in general, data sets don't just live in 2 dimensions, they live in extremely high dimensional spaces. And so for that reason, it's very useful to be able to train computers to be able to deal with this high dimensional data that our visual cortex can't give us a quick way of processing. Now, I should mention that this type of algorithm that I described over here isn't the entirety of machine learning. It's probably the widest class of use cases, and this is known as supervised machine learning, where what we have is we have a bunch of examples, red and blue examples, and we're told what the true label is. And our aim is then to figure out on an unlabeled data set what the actual labels, in this case, red or blue, would be for those unlabeled examples. But in some applications of machine learning, we don't actually have ground truth labels. Like, for example, the data I gave on the right, what this ends up showing is this is just a set of points, right? But what we would like to do is we'd like to be able to build a model which we could then potentially use in a supervised learning algorithm later, but it's not necessary. But we'd like to be able to build a model to be able to roughly describe the structure of these points. And an example of a great algorithm for doing this is k-means clustering, which provides a way of breaking up the data into k-clusters in such a way so that it minimizes the sum of the variances inside each of the individual clusters. And so by running this algorithm, you can end up seeing that the data on the right ends up actually kind of being nicely clustered into 3 meaningfully different clusters that actually look reasonable when you take a look at the data. And so from this perspective, machine learning can also be used in order to help provide us with insights into complicated data distributions that we may not be able to visualize or understand just by staring at it. Okay, and so this, of course, the final example that I wanted to give is a supervised example that commonly ends up being used. And so as an example, we can end up using computers in order to be able to classify images in the following way. What we would do is we would take, say, an image. In this case, these are handwritten digits taken from the MNIST data repository, which is just like a list of, thousands of handwritten digits that people put in. I think Jan LeCun and his graduate students, if I recall. And the basic idea is that every pixel inside these images is then recorded as an individual feature and stored as a grayscale value between 0 and 255. And so those values over here now become the analog of those features, like the X and the Y that you end up seeing in this. Except now what you've got is I believe, you've got 768 dimensions for the data for every single image, because that's the number of pixels that you have. And so the way that computers end up dealing with this is they translate these images to a huge dimensional space. And then we feed that into a machine learning algorithm, like a neural network or support vector machine or some other solution, in order to be able to train it so that when it is provided with a new image that it hasn't seen before, it'll be able to output the label corresponding to that. Okay, so that's the basic idea behind this. And so what we'd like to be able to do is we'd like to be able to solve this problem or these sorts of problems on quantum computers. And there's a number of tools that people use again and again and again for these types of algorithms. At a high level, one of the biggest ones that people end up using is amplitude amplification. And the idea behind amplitude amplification is it's really a technique for, the way I like to think about it, monkeying with probability distributions. So if you have, for example, a uniform probability distribution over a bunch of different outcomes, what we can do is we can apply amplitude amplification to modify the probability to push all of the probability into the outcomes we want. This can be used in order to search as well as to speed up, for example, finding the closest vectors to other vectors, which ends up helping with algorithms like clustering and other type applications. Another approach that's been used quite a bit is adiabatic optimization. And so the basic idea behind this approach is what we do is we end up defining an energy function. So for those of you who've done a little bit of ML, this is like, a form of, you can view it as a form of Hebbian learning. But the basic idea is that what you do is you take an energy function and you choose it in such a way so that the outcomes you want correspond to the minimum energy of this system. And then if you begin with some toy, easy to prepare, energy function, and you slowly vary that over time into the true energy function that you want, the quantum system that you began with will end up in the minimum energy configuration of the problem system that encodes the answer to your problem. And so this has been proposed for algorithms like clustering and neurocentroid classification, as well as a number of other applications. And its descendants end up showing up in the form of various flavors of quantum neural networks. But that's one of the fundamental ideas. The next one that ends up getting used all the time is linear systems. In particular, quantum algorithms can actually give, with some major caveats, exponential improvements for solving linear systems of equations. So for example, if we can write our machine learning problem as a linear systems problem, like AX equals B, then we can use a quantum computer to invert the matrix A in time that's exponentially faster than the best known matrix inversion algorithms, under the assumption that A is sparse and well-conditioned. So that, for example, is something you can do because you can write the least squares fitting problem as a matrix inversion problem of this form. So by converting least squares fitting over to this, you can find nearest vectors, and you can do things like, for example, train support kernel SVMs exponentially faster in principle using this type of technique. So these are some of the ways that we end up approaching using quantum computers in order to be able to provide advantages for quantum algorithms. So just to give you an idea about what type of advantages we can expect from this, for these types of algorithms, we expect like an order square root n speed up. So if a task would end up requiring n queries or operations, we can do it with quadratically fewer operations here. This over here, unfortunately, is, big O question mark, which I really think, is, I really think that we need to have, something in Bachman-Landau notation to talk about something that we have no clue about what the complexity is. The reason why is that the complexity of adiabatic optimization, this ends up depending on the minimum gap between the energies for the minimum energy configuration and the first excited configuration. And so in order to figure out how slowly you're going to have to move through this, in order to make sure that your quantum system doesn't move so fast that it accidentally jumps the track and goes to an excited state, which may not necessarily encode the answer to your problem, you need to know what this gap is at every time during the process. And this problem of finding the gap is actually often harder than the problem of the machine learning problem you're trying to solve. And so this ends up, in particular, making it very difficult to quantify the improvements that hardware such as D-Wave, which operates under similar principles, ends up performing under these circumstances. And some forms of quantum neural networks that are based on trotterized adiabatic ideas, this same sort of idea ends up showing up. So in many cases in quantum machine learning, although people end up proposing these types of algorithms for it, we really actually don't know how well they'll really perform. And so this is an open question that that exists in the field. With this over here, the time that we end up needing can actually be logarithmic. So it can require an it can acquire an exponential speed up. The big problem is, as I'm going to mention, is that there's a number of caveats and big important caveats that end up coming in here that can actually end up reducing the performance of these algorithms from an exponential improvement like we'd like to see to something that's kind of more like order, n to the 1/3 or something like that in most realistic cases. So those are the basic ideas behind it. And the final one that I really, want to mention, of course, is close to my heart, is quantum simulation, which is often used as a paradigm in order to be able to solve the linear systems algorithm. But ideas from quantum simulation are also used in order to be able to build quantum neural networks, in particular quantum Boltzmann machines, as well as some classes of feed-forward quantum neural networks. Okay, so just before continuing, I really want to, make sure that you know these three things. So these are very, very important challenges that end up existing whenever you try to build a quantum algorithm to end up solving any problem in machine learning or data science. And the first and arguably most fatal problem for many applications is what is the so-called input problem. And the basic idea is the following, right? Like, let's take a look at solving the problem AX equals B, okay? So in order for us to be able to solve AX equals B on a quantum computer, what we need to be able to do is we need to be able to have two things. We need to have an algorithm for computing the matrix elements of AXY. Okay, and this algorithm, ideally, in order for this to be practical, this has to run in time order polylog of the dimension of the system. So order polylog 2 to the n in our case. Also, we have to have, in order to run use a quantum algorithm to solve this problem, we have to be able to prepare the state B. And B over here, this is a vector in C 2 to the n. So there's 2 to the n different numbers in that. And just from a counting argument, you could end up seeing that the number of gates that you're going to need in order to make a vector in general with 2 to the n elements is in, you guessed it, order 2 to the n. So this is a very weird problem because classically, right, inverting a matrix is the most expensive step in solving AX equals B. Well, in this case, we can actually, if an algorithm for computing a matrix elements ends up existing and the condition number of that matrix isn't too large, then we can actually do A inverse cheaply. However, creating B over here is expensive. And so what this ends up meaning is that basically we end up running into this problem where the state preparation ends up actually preventing the possibility of an exponential speed up. So this problem ends up being ubiquitous in ML applications because often either B or A over here, either one of these matrices, and it usually ends up containing your training data. And so if we wanted, basically what this ends up meaning is that we either need an algorithm for generating the data that we're training the quantum system with, or we're going to have to literally bring this in as a lookup table. And the cost of that is going to be order 2 to the n. And so for many machine learning tasks, this strategy of trying to get exponential speedups is actually really dangerous. So the moral of the story is people spend a lot of time making noise about quantum algorithms for big data. These types of arguments suggest quantum is not awesome for big data. All right, just because of the fact that you got to load that data into the system, and that can be a profound bottleneck for problems. It doesn't rule out polynomial speedups, mind you, but it does forbid exponential speedups for most of these applications. The next problem that people you need to think about is how expensive is it to get the output from the quantum system? So if we wanted to do something like solve AX equals B, right? Well, we would say, if we wanted to do this in the quantum land, we would say the quantum state X is at least proportional to the inverse of the matrix A acting on the state vector B. Okay, cool. We got a solution out. But the problem is that that solution is a quantum state vector. And a quantum state vector, for example, like 1 over root 2, 0 plus 1, if we wanted to learn this particular state vector, we'd have to do it by sampling. And in general, the number of samples that we're going to need in order to be able to estimate this guy is going to be polynomial in the dimension and 1 over epsilon, where epsilon is the error that we're willing to put up with it. And as I said before, if we want to do this for a high dimensional data set, well, that dimension is order 2 to the n. So this ends up meaning that the output problem can end up meaning that reading the output from these quantum algorithms can also ruin your potential for an exponential speedup. However, this problem is the easiest to get around by changing the definition of your problem. So for example, if you don't need to know the answer, but you need to know some function of the answer, like its mean or something like that, then you could completely sidestep it. The input problem is a lot more challenging. And the final of the 3 problems that ends up showing up is the benchmarking problem. And this problem is a major issue, because going back to the previous discussion, right? For many machine learning algorithms, they're heuristic, like adiabatic optimization, and where we don't necessarily have meaningful performance guarantees on how well the algorithm is going to work in a particular instance. So what that means is we've got to benchmark it. But the problem is we don't have good enough quantum computers in order to be able to benchmark meaningful scale problems in the machine learning space. So the problem is, well, how can we actually come up with convincing arguments that the performance of the algorithms is actually going to be worth it? As in, like, how do we convince ourselves that if it were to cost $1 billion for us to be able to build a quantum computer to solve real world problems in machine learning, how do we know whether or not it's going to be worth doing that or spending $1 billion to end up building a number of large data centers to do it? And so this is one of the big challenges. And to date, for heuristic algorithms, nobody really kind of deeply understands how well many of these heuristic algorithms are actually going to work in practice for large quantum data sets. Now, the final thing that I wanted to bring up is a second part of this benchmarking problem. And this is these papers that you and Tang put out were really kind of touchstone papers in this space, because of the fact that what it showed that often the algorithms that people would compare the quantum solutions to these for are not actually the right classical analogs of the quantum solution. And so Ewan, in a series of kind of landmark papers, she ended up showing that classical randomized algorithms can actually match the exponential speedups that have been purported for many existing quantum algorithms. And that was just because the people proposing it weren't thinking clearly about what the right classical counterpart was for the quantum algorithms. And so this is very important. When you're thinking about an algorithm for solving machine learning problems, and you see that it might have the potential for an exponential speedup, you need to really be able to compare against all classical algorithms if you can help it. And looking at classical randomized algorithms often ends up giving you ways or analogs that are far closer to quantum solutions than most of the stuff that people presently use in libraries like PyTorch or TensorFlow. So in order to think kind of a little bit more clearly about how we should go about approaching problems in quantum machine learning, I wanted to spend some time about talking about how to encode training vectors, which again represent like the data that you input into a machine learning algorithm, how to represent those in a quantum world. Now, there's two different types of encodings that I want to describe. The first encoding is perhaps the most obvious, but ironically the least used encoding of data in quantum machine learning. And this is what I call a bit encoding. And the basic idea is that, let's say what you have over here is you've got a, image that you want to learn from, right? I am a horrible artist. So let's say this is an image, right? And, we're doing this just like we would with MNIST. We break it up into a bunch of individual pixels. And every, let's just deal with binary data over here. So every pixel that contains, say some ink, I'm going to shade in, okay? So each of these pixels contains 1 or 0. So we can end up encoding then this image as a bit string just by saying, okay, this is going to be 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, so on and so forth. And so what we would do for quantum bit encoding for this is we would just say, okay, well, the input that we're going to feed into our quantum algorithm to describe this image vector is just going to be 0, 1, 0, 0, 1, so on and so forth. Actually, I think there's 3 zeros in here if I take a look at that. But in any case, you get the idea. So for every bit that we would use in a binary encoding of the feature vector, we end up allocating a qubit in our quantum algorithm. And then we can have superpositions over these different bit encodings. And then all the power that we end up getting from a quantum model for the data is then delivered just by these coefficients over here. So the one that people, though, use much more frequently is I feel, the less natural encoding for the data, but it's easier in some sense. And this encoding is known as amplitude encoding. And the intuition behind amplitude encoding is actually also kind of slick. What the idea basically is that if we've got a vector over here, let's say this vector of bits is V. Well, in quantum computing, the natural objects that we normally think about are, state vectors, V. And so instead of taking the bits over here, how about we choose our state vector to be proportional to the bit vector that we end up getting up here. And the number of quantum bits that you need in order to do this, let's say this was, we used 784 pixels in order to do this. Then with a bit encoding, we would need 784 qubits. And to give you an idea, the largest quantum computers that we can really get access to right now are 53 qubits, which, by the way, is incredibly impressive compared to what the quantum computers were when Gibran and I were going through our PhDs. But in any case, the key thing is that we cannot fit 784 qubits inside existing computers. However, if we take a look at the number of qubits that we would need to encode this just using this amplitude encoding, we would need log base 2 of 784, which is less than 10 qubits. So we can fit these vectors in a quantum computer by using an amplitude encoding. And so what I wanted to do is something that actually I think is pretty hard to find in most of the literature. I wanted to talk about the pros and the cons of these two types of encodings and argue that, well, amplitude encoding can allow you to fit much bigger vectors in your system. If you can afford it, you'll almost always want to do a bit encoding because there's some serious drawbacks to encoding your vectors as directly as quantum state vectors using an amplitude encoding. So to give you an idea about the encoding for vectors, one of the things that that we end up coming up with is that quantum state vectors are always unit vectors, but not every vector used in machine learning is a unit vector. And on top of that, the length of the vectors that you end up using, it can be meaningful. So for example, let's say what I had is I had the following data set, right? I've got these X's over here, and I have these O's. And I'd like to be able to build a classifier between X's and O's. Now you can see that we could end up building a perfect classifier for this by drawing a circle around the O data set and it going out. And the main difference, if we set the center of our coordinate system to be there, between the X's and the O's is actually the length of the feature vector with respect to the center. So the lengths of vectors can be crucial for classifying data in a classical setting. So in a quantum setting, we need to find ways of being able to encode that. And the way that that you can do this within an amplitude encoding is by breaking up your state vector into two parts. This part over here, I know this looks a little bit confusing, but this part, think about this as just being the direction that one of these feature vectors is pointed in. So this is the unit vector that corresponds to each of these individual X's, say, that I've drawn in the diagram. This part over here encodes the length of that vector as a fraction of the maximum length that you could end up getting. So this over here is just this is the length, and then this is the direction. So you can think about this as sort of a analog of a polar coordinate system that's being formed, where we're keeping track of both the direction that a vector is pointing and the length of that vector. Now, one of the things that's interesting about amplitude encoding is if we want to be able to create an isometry, we want to be able to create a angle preserving map between the training vectors that we're using for a real ML problem and the quantum states that we're using in a quantum classifier, we actually have to encode the adjoint of a vector differently than the adjoint of its encoding. The reason why is that the inner product of a vector with itself over here is going to depend on the length of the vector. However, if we take this quantum state vector and took the inner product of it with itself, we would always get 1. And so in order to make sure that these vectors have the correct inner products with themselves, we actually need to encode the adjoint of the vectors in any machine learning algorithm differently than how we encode the ordinary vector. But that's kind of a little bit of a technicality, I suppose. And you can go through and end up seeing that if you do this encoding, that the inner product literally is just actually the true inner product normalized by a constant. Okay, and so the interesting thing about this is that we've got to ask ourselves, okay, if we're going to use amplitude encoding, which is, as I said, what the vast majority of heuristic algorithms in quantum machine learning use in order to represent their data as quantum bit strings, we have to ask ourselves, just like you when asked, what's the classical analog of this algorithm? And so one of the things that you can see about this is that actually vectors that are provided in amplitude encoding in some cases can be exponentially weaker pieces of evidence than a vector that's applied given in bit encoding. The reason why is because of the fact that if we got as input one of these encoded vectors, and we envisioned measuring it, we wouldn't get the entire vector back. So it's not like, the smiley face example, right? If I measured this quantum state that encodes the smiley face, right? What would happen is I would get a pixel, say maybe this one, with some probability, depending on the amplitude that's assigned in the amplitude encoding to each of these. If I wanted to reconstruct this entire training vector exactly, I would have to get an infinite number of samples, i.e. an infinite number of copies of the training vector to be able to do that. However, if I had it in bit representation, I'd be done. So for some problems, even just the simple problem of asking, what is my training data? Amplitude encoded training data in the quantum computer is actually vastly weaker than the bit encoded version of it. And so for this reason, you could sometimes actually lose a lot by using these encodings. And in fact, there's results from quantum information theory that can actually prove lower bounds on the number of samples that you need with an optimal learner in order to be able to distinguish between two concepts. And with amplitude encoding, you can show, in some cases, you need an exponential amount of evidence in order to be able to distinguish between two classes. And so the example that you can use specifically to do this, I won't go into too much detail about this, but the problem, imagine you wanted to classify bit strings based on parity. So you'd like to be able to say, okay, I've got two concept classes. One is the set of bit strings that have odd parity, and the other is a set of bit strings that have even parity. And I'm going to use an amplitude encoding for doing it. So using this approach that I discussed previously, if we wanted to get this bit string over here, which has even parity because there's an even number of ones, this bit string would be represented as the following quantum state vector over here. And so if we consider, say, an odd one, which I've found by flipping that guy over here, this is the odd bit string. Now, it looks very similar, except it only differs in this as well as a couple of the amplitudes. And the inner product between those two is about 2/3. And in general, if we ended up doing this, not just for this this simple like 3 qubit example that we're looking at here, if we wanted to do this for computing a parity of n bits, the fidelity between the two isn't just going to be 1 minus 1/3 like it is for the 3 qubit case. It's going to be 1 minus order 1 over n. And so basically what we end up getting over here is that if we want to be able to compute the parity for a very, very long bit string using this, we will end up needing exponentially many samples in this particular case. And so whereas distinguishing between these two for very long bit strings is trivial, actually, if we have the bit encodings. So the moral of the story is that amplitude encoding looks like you're getting a free lunch. But the moral of the story is there's some profound limitations in what you can do with it. So the next thing that I wanted to do is I wanted to spend some time talking about what input models we end up providing. So after you've picked a particular encoding for the data that's coming into your quantum algorithm, you need some way of loading that data inside the quantum system. The simplest version of this is what I call a density operator oracle. And basically what the idea behind this oracle is that you put in some fiducial state, say 0, and then it will output a mixed state over all of the training vectors that are feeding into it. So this is an analog you can envision of like an experimentalist randomly just choosing one of the training vectors and feeding that into your quantum algorithm. So this is the most natural way of doing this. However, this is less powerful than a slight, improvement on this, which is a unitary oracle. A unitary oracle doesn't just give you the ability to have like a probability distribution fed in that's uncontrolled over the individual training data. What it allows you to do is it allows you to programmably control it. So you put in a index or a training vector J that you want to be able to prepare, and then it prepares just that training vector. And so the basic idea is that this unitary oracle is actually more powerful than a density oracle, because you can simulate a density oracle with one query to a unitary oracle, but you can't simulate a unitary oracle with one query to a density operator oracle. So now that I've discussed, the oracular inputs that we end up getting to it, and they're all basically of those two forms fundamentally. Let's talk about how to build a particular classifier. So let's say what we wanted to do is we wanted to be able to build a quantum analog of the support vector machine. So the idea is, imagine what we wanted to do is we had these individual data points over here, these green and red data points. And what we'd like to be able to do is build a quantum circuit that's capable of discriminating between these points. And I've drawn these literally in the block sphere here. So the idea behind this is that if we wanted to build an elementary classifier for this data, what we really have to do is we have to be able to figure out a measurement that we can perform that will, with high probability, be able to distinguish between this data. And the way that we can do this is by envisioning this measurement operator that we're carrying out ends up looking like the following. We apply Ry of theta. We've got like psi in coming in over here, and then we measure in the end. And what we want to do is we want to be able to choose theta to maximize the probability of success, i.e. of successfully classifying an unknown point as being either red or green. And so the way that we do this typically for most of these quantum algorithms is we will take a look at variationally improving it. So we would rotate this, increase its value of theta, and use gradient descent in order to be able to find the angle that gives us the highest probability of success for classifying our training data, which would probably be some angle around here for this data set. And so this is great, but of course, the number of samples that you end up needing ends up scaling with the dimension of the gradient that you need. So in this case, it's just a one parameter model. But if you have d parameters in your model, the number of samples that you need in order to be able to compute the gradient scales linearly with the dimension and like the inverse square of the accuracy that you need the gradient. So this essentially is the idea that most people end up using in quantum machine learning to be able to train quantum models for data over here. And so that simple 1 qubit example, of course, is kind of woefully, inadequate for solving most problems. And a common sort of paradigm for this that's used is this particular form where each of these G's over here, these are an arbitrary U1 rotation. So this is arbitrary single qubit rotation, and these are arbitrary controlled rotations. So for each of these, we would have 3 parameters. And for each of these, because global phase matters for controlled operations, we would have 4 parameters. Okay, so this ends up giving you a large number of parameters. And the basic idea is you feed in, quantum analog of your state vector over here, like I drew over that, in these bits. And then you find the angles corresponding to all of these such that the probability of 0 is max here for states in class 0 and min for class 1. So basically what we do is you just do gradient descent on these parameters in order to be able to find the best classifier that you can out of it. And so, in this particular case, because amplitude encoding was used, we ended up going through this and ended up finding that on standard examples, these types of networks perform okay, but they actually don't necessarily end up performing that much better in practice to even actually relatively simple classical machine learning algorithms, albeit it's worth noting that this was using amplitude encoding, whereas the classical algorithms had the advantage of bit encoding. And something that people haven't done to date is actually taking a look so much at what the performance of classical algorithms are if you give them a probabilistic feature vector rather than a deterministic one. So the comparison here is perhaps a little bit unfair, but even at that, quantum is doing reasonably well. And so, yeah, let me just actually jump ahead past this. Another approach that is popular is what's known as a quantum autoencoder. And this approach is actually, I think, really kind of cool. The idea behind it is that what you do is you try to train a quantum channel that ends up taking in a density matrix from a particular class and puts that through an encoder. It then traces out half or some large fraction of the quantum state and then feeds the rest of that quantum state through a decoder. The decoder then takes the result and then ends up outputting a copy of rho. The thing that's cool about this is that you can actually use this also for feature completion. So if you end up viewing your quantum state vector as being a state that's of the form psi tensor label over here, what you can do is you can basically drop the label part and use the autoencoder in order to be able to generate the quantum state vector and the label, even though you've kind of thrown out the quantum state vector along the way. And so this is the quantum analog of methods that are used, kind of like what you've seen maybe for quantum deep dream, which is a way of generating images based on a bunch of training examples. So the question, I guess, is theoretically, okay, well, what's the best that we can do for the gradient descent optimization for both of these types of algorithms? And the moral of the story is I don't want to get into too much detail about this, but what you can do is you can use quantum algorithms actually in order to be able to speed up the gradient calculation process to begin with. And you can get a quadratic advantage, as in it goes like the square root of the dimension of the gradient vector rather than linearly with it. And it goes like 1 over the uncertainty using it. So quantum algorithms can actually be used to do the gradient descent or compute the gradients faster than naive measurement would allow. But often people don't end up using these techniques because it requires dramatically more quantum bits than the existing approach. Although asymptotically in the long run, this is probably doing something like this is probably what we would want to do if we want to do quantum machine learning on a realistic quantum computer. Now, I talk about computing gradients because a big problem that ends up actually coming up in quantum machine learning is that gradients tend to decay in high dimensional spaces. And so recent work that was done by some of the folks at Google ended up showing that if you take a look at high dimensional spaces, you can actually argue generically what the size of the gradients are. And their work ends up showing that the variance over here is actually exponentially small, where n is the number of qubits, meaning with extremely high probability, if you end up picking a particular point in for your initial parameters for a quantum neural network, say, then the gradients that you'll end up finding for those parameters will be essentially zero, which means that these algorithms will, generically speaking, take exponentially long to train. Now, even with if we end up using some of these fancy gradient algorithms over here, the number of operations we need to estimate the gradient within air epsilon goes like 1 over epsilon. So having gradients that are exponentially small means even if we use the best available methods, we need an exponentially large number of samples to be able to deal with this. Now, some of these problems don't show up for classical machine learning, in part because of the fact that everything is a bit encoding there. There, if you need more precision, you just throw more bits at it. Double precision allows you to have a ton of bits of precision. And this is kind of sort of one of the ways that backpropagation ends up saving the day for the gradient decay problem. But here, we don't have that luxury because of the fact that so much of the model is stored in probability, not in bits. So these problems are a vital, vital problem. Another thing that I wanted to mention is that recently, my colleagues and I ended up showing another form of problem that can come up with quantum neural networks. In particular, imagine what happens is if we picked half of our qubits to be so-called hidden layers. These are layers in a neural network that are just used to generate correlations, but not directly used for the output. It turns out that if entanglement, too much entanglement ends up building between the hidden layers and the visible layers, when you ignore, or in the language of quantum computing, trace out these guys, you end up actually having a state over here, which ends up becoming the uniform distribution over all outputs. And so essentially, quantum mechanical entanglement inside your neural network, while people previously had thought it was a big boon, these strong correlations actually are where the majority of the data in the network is stored. And by throwing away some of your data, you're now accidentally discarding relevant data that the model needs to be able to classify. And so this ended up showing that actually, if we really want to build good quantum models for data, we need entanglement, but we need to use it surgically. Because if we just allow it to build up any way we feel like, this entanglement will actually destroy the ability of a model to predict. And actually, it'll become worse than a classical model if you do that. So one of the last thing that I wanted to talk about is a avenue that my colleagues and I have been looking at in order to try to address this last issue. And it is a generative quantum pre-training. And so the idea basically goes back to generative training classically. And so the idea basically is that what we'd like to do is we'd like to be able to train a classical model with a bunch of examples and get it to generate new examples that are typical of this. So here's some early work from Salakutinov and Hinton back in 2012, I believe. And this was using a model of a quantum or classical neural network known as a Boltzmann machine. It was trained with those images on the left. And then after it was trained, you could actually just set it up, and let it run. And it would dream up new instances of the images that it ended up seeing. And these the examples that it generated are the ones on the right. And so, you can, we'd like to be able to do the exact same thing, except instead of getting the system to generate new vectors like it was doing here, we'd like to train a quantum model with quantum state vectors and get it to generate new quantum states. And so the basic idea behind this that we want to do is we want to be able to follow a very similar model to what I showed previously, where we're carrying out a sequence of operator exponentials acting on, say, some fiducial state, like the zero state. And then we'd like to be able to figure out the values of theta that end up causing the output state after we trace over these hidden layers, i.e. part of the quantum system that we're only using to generate correlations, in order to be able to get the output state from this model to be as close as possible to the input state. And so there's many different notions of how to measure distance in here. The one that makes the most sense from an information theoretic perspective is this notion called the quantum relative entropy, which is like the analog of the KL divergence, which is sort of a measure of the amount of quantum information you need to encode samples from one distribution given copies of the other one. And so the quantum relative entropy is given by this expression down here. And it's really nice. It's related to, you can bound the amount of number of copies you need to be able to discriminate two states using this. But unfortunately, it's not symmetric, and it's actually very difficult to differentiate, it turns out, because of the presence of these matrix logarithms. And so in practice, what my colleagues and I have looked at in order to try to be able to find good ways of generating these states is by taking a look at Rayleigh divergences, which are given upper bound on the quantum relative entropy. But the thing about it is that it has ordinary matrix logarithms in here. And for the case of alpha equals 2 over here, it reduces to something that's a lot simpler. The logarithm of the trace of the square of the input density matrix rho multiplied by the inverse of the training data sigma. And so basically what you have to do with this is if you've got a training data set, which is described by a density matrix, for example, something that would be fed by a density matrix oracle, you would then compute the inverse of that density operator, generate that, and compute the trace over here. And this actually can be differentiated. The amazing thing about this is that actually we can go through and compute the derivatives of this. And unlike the conventional approaches that people end up using for training, based on fidelity or other sensible like expectation values of observables, the number of operations that we end up needing, the size of the gradients when we average over the Haar average for this is actually not necessarily exponentially small. And so what this ends up saying is that actually we can train these types of models for quantum data in a way that doesn't seem to necessarily be susceptible to the gradient decay problems that we ended up seeing elsewhere. And this is an amazing, I feel this is kind of an amazing sort of discovery, because what it means is it says, okay, say we want to learn some structure of arbitrary quantum states. Like if we wanted to do a machine learning problem, like classify states as either, say, being a ground state of a molecule or being an excited state of a molecule, what we would do is we would first begin, in order to get around these gradient problems, by training it to just generate ground states and excited states. Because these models over here don't have exponentially vanishing gradients, we can use this to warm up quantum machine learning algorithms. And then once we've got it vaguely producing something that's sensible, then we can switch over and do the conventional approach for this. And so this is potentially a way that we can do this, but also it opens up a new opportunity for people to think about tasks that we can do in a quantum setting. So one of the big tasks that we run into that's challenging in a quantum setting is state preparation. If we have an arbitrary state that we need to be able to prepare, it's often very difficult to be able to find a good circuit for building it. This generative training approach allows us to find a method of preparing a quantum state that we've trained the network with through gradient descent. And to give you an idea about how well this ends up working in practice, here's an example of that we ended up generating for these quantum neural networks that I discussed over here, like these guys, to see how well these actually can end up generating random thermal states. And what we ended up finding is actually something kind of remarkable, that if we provided it with enough hidden units in it, basically we were able to more or less exactly prepare the 3-qubit thermal states that we were training the model with. And the wonderful thing about this is that most of the time, due to this entanglement-induced barren plateau problem that I mentioned, increasing a number of hidden units for quantum models, i.e. the number of qubits that we're just tracing over or ignoring, ends up making the model worse because of the fact that we're throwing data away due to entanglement. But this approach actually benefits from hidden layers, just like classical machine learning does. And so this is something that, that I feel ends up showing a big step towards how we can think about approaching problems, particularly generative problems, in a quantum domain, and is an important stepping stone, I think, to us having a complete picture of what machine learning ought to look like or could look like when we're dealing with problems that are where the data is not fed in from the classical world, but rather we're trying to learn properties of unknown quantum systems, or perhaps subroutines inside a larger quantum algorithm. And so basically, I mean, to conclude, I've covered a lot of the kind of sort of foundational tools that end up going into quantum machine learning, and spent some time on some more recent stuff towards the end. And basically the idea is that machine learning tools increasingly are going to become more and more important for us probing the nature of reality at a quantum scale. We can also end up getting speed ups for certain classical models. However, the best provable speedups that we have for classical models tend to be polynomial. I mentioned, but unfortunately I cut the slides, that, that also other applications are going to be important as time goes on. And the advantages that quantum computers have for security and privacy are actually going to also translate over to quantum machine learning. And the development of these ultra secure as well as increasingly powerful models, especially for describing quantum data, potentially could be game changers. However, we don't understand yet how well these models are actually going to impact classical data. And certainly at the moment, there's no clear evidence for exponential improvements that are going to be meaningful. But to me, the big questions that I'm most passionate about in quantum machine learning is I really want to know what quantum machine learning even is. I want to know what it means for a quantum agent to learn. I want to know what we can learn, how hard it's going to be to learn, and importantly, yeah, what it means to learn in the first place. Thank you very much.
Thank you very much, Nathan. That was wonderful. And so I'll share the question sheets.
Okay, cool. So I see a question popping up. Well, Gibran's stuff is coming in. So there's a question that ends up coming up, right? Where people often these days will talk about expressive powers being the most important thing, i.e., how high accuracy can you end up getting as a function of the number of parameters for a quantum model versus a classical model for a data set. And at some level, people often, unfortunately, really like talking about it is in computational complexity is totally pointless and expressive power is the only thing we care about. And that's kind of coming from an ML-centric perspective. But what I would say is I would say that at some level, it's essential to think about the computational complexity of this because, well, if we're not, then why are we doing this on a quantum computer? Why not say, okay, well, we can just spend exponential overhead, simulate the quantum model on a classical computer and run with that. So at some level, the two are intimately linked, and figuring out, what the trade-offs are going to be given a level of accuracy that you end up needing and computational restrictions. And figuring out how to explore that trade-off space, that's part of what the whole field's about, really. But in any case, I've got the people who were waiting more patiently than the questions that just popped up. So the first question is, okay, go ahead.
Right. So this is something that came up right in the middle of the talk. So when you talked about the energy minimization approach, so the question, Shakir wanted to know what kind of problems are possible to transform to energy minimization.
Right. Formally speaking, just about anything. The main reason is that actually we can embed an arbitrary quantum computation as an energy minimization problem, it turns out. But the largest class of optimization problems that are naturally easy to focus, to phrase in that particular way, are like quadratic unconstrained binary optimization problems. That's kind of like one of the biggest families that ends up coming up that's easy to do. However, basically any SAT problem can be directly mapped to an energy minimization problem. So in principle, if you can take any problem in NP and map it directly to an energy minimization problem. So more or less anything, really.
So I had a question also about kind of the benchmarking challenge that you mentioned. This seemed to come up also when kind of students who start working on some small project related to QML. So if some student or some person has worked on a project and they end up with a quantum model that they've run on available simulators, and they now want to be able to compare it against, well, what are the best classical heuristics available? What's a good resource to be able to do that comparison? Is there a kind of a learning zoo out there, kind of like complexity zoo, where you could say, hey, here are the known benchmarks?
Yeah. So one of the things that, of course, is worth taking a look at is there is the UCI repository. That's something that I often end up using. It's got a list of standard data sets that you can end up porting over to the quantum setting. Biggest challenge with it is dealing with the right way of encoding that some of the data examples over, because for all but the smallest examples, it likely won't fit inside the simulators that you can run. But that's often what people will end up doing. And those benchmarks that I ended up showing, those were examples taken from there. So I'd strongly recommend taking a look at that. And there's also an analogous set of problems for reinforcement learning, if folks are interested in that.
You mentioned the generative objective function approach, kind of avoiding the barren landscape plateau problem. I wanted to figure out how does that compare to, or how does it avoid the plateau when compared to entanglements not being able to avoid the plateau? So what kind of entanglement does this approach kind of generate such that it avoids that plateau?
Yeah. So the reason why it fundamentally ends up avoiding this is actually it doesn't. That problem, the entanglement problem, is kind of fundamental, and it will end up leading to really bad models in general, right? Because basically, if you have too much entanglement between your system and a subsystem, when you trace it out, you're just going to get the maximally mixed state. And so and in general, generic quantum states are nearly maximally entangled. So that's the origin of the problem. But the thing is that the entropies that we're taking a look at have these pesky logarithms that I mentioned in them. And the logarithms have a divergence near zero. And so in these examples where the overlap or the model is predicting horribly, normally you get trapped in a region of nearly zero gradient. But the logarithmic divergence here actually ends up working to your benefit and allows you to get a meaningfully large gradient to escape from that.
Thank you. So there are a couple more generic questions, after which I'll go to the Zoom questions, which although are a bit more relevant to the talk. So most of the generic questions talk more about kind of where do you see the field kind of approaching or developing into. And the second kind of part is about people who are starting in quantum computing or quantum machine learning, kind of recommendations for how they can overcome the challenges that you expect people to face when they start in this area.
Sure. So let me begin real quick with the cloud computing question, which I think is an easy one to address. At the moment, the way that people are envisioning quantum computers, because most of the most successful quantum computers have to operate inside a dilution refrigerator at temperatures of about 15 to 30 millikelvin. And we cannot fit that on a desktop. So for that reason, most of the quantum computers that we've been looking at at least for the foreseeable future, are going to be cloud accessible resources. So the way most people are seeing quantum computing right now is just another resource that's deployed in the cloud. Just like you would have, GPU, CPU, maybe FPGA resources deployed in the cloud. We'll also have quantum resources that people can end up getting for particular tasks. Now, the question about what pace is this developing at? The pace is stupid right now. So just give you an idea, I thought that we would be looking at maybe a 50 qubit quantum computer by the time I retired. Okay, we've got a 50 qubit quantum computers that are borderline publicly available by IBM right now. Let alone the stuff that's going on behind closed doors. And on top of that, the IBM is committed within a few years to be able to produce 1,000 qubit quantum computer, which sounds amazing, but it's important to recognize that the errors in these quantum computers are sufficiently bad that you wouldn't even be able to do a sequence of controlled NOT gates across the entirety of that quantum computer before this quantum state would die. So the real task right now is for us to be able to take these quantum computers and build quantum error correcting codes to allow us to build long-lived quantum memories that could last for seconds, maybe even hours, despite the fact that existing quantum computers can only keep information alive, depending on the hardware, on the order of hundreds of microseconds. And now, as for, there was another question about, what was it again? It was
how to start out in the field. Mathematical challenges that people face when you start out in quantum machine learning, conceptual challenges.
Right. So there's, the best ways to begin with this. I'd recommend taking a look at my review paper just to give you kind of like an idea of what the landscape ends up looking like. But the next part after that is the harder part, because there's kind of two different ways that people approach it. I tend to approach machine learning from more of a theoretical perspective. There's other folks who approach it from kind of more of an empirical perspective. You've got to decide, which of those two approaches is kind of closer to your style. But make sure that if you go down the empirical route, that you know enough about the theory to understand the importance of computational complexity, and also the importance of no-go results, such as these limitations proven that information theory ends up giving, because it's really necessary for you to be able to understand and contextualize what the empirical models that you're providing are doing. The other thing that I think is very important is recognizing how hard doing good empirical work actually is, because you need convincing data sets. And it is very, very hard to make a convincing argument about the importance of a heuristic from examples that are done with 5 bits and smaller. So, it's hard work, but, if you're careful and methodical about it, there's a lot of good stuff to be done. And there's a lot of open questions about really what ideas are practical and what ones aren't.
So these are now the Zoom questions.
Yeah.
How promising is it to automatically learn an optimization algorithm that works well for quantum landscapes instead of using manually designed one like Adam or an evolution research?
Okay, so basically so if we're taking a look at classical optimization, in practice, most of the time, the quantum only gives modest advantages for this. So for the gradient evaluations that we end up using, you can for continuous optimization problems like these ones, you can end up getting quadratic advantages using quantum algorithms for gradient descent. And by using Grover search type approaches, you can get speed ups in terms of the number of random restarts you need for searching for a global rather than a local optima. But that being said, these are kind of modest advantages. So the real cases that you really want to take a look at, I feel in the quantum world, are places where you're trying to optimize an objective function that's hard to compute classically. So, doing something like minimizing an energy that would require exponential resources to compute classically. That's something where comparing and contrasting these is good. And in those cases, Atom is used all the time in, say, variational algorithms for finding the ground states of chemicals.
So I think we can go through quickly. Can we solve the exponential problem by using ancilla? I'm not sure which exponential problem is being referred to over here.
Okay, so the input and output problems most likely, given that time, I'm assuming. But yeah, no, you really can't. Unfortunately, not in general. You need to focus your attention on very specific problems rather than having general solutions for it. And the big problem is that for exponential speedups, we don't know the specific problems that are practical that actually conform to the assumptions that we need for an exponential speedup.
Ahmed asks, can we kind of process the whole training data using just Hadamard transform and all the data?
We can, but this ends up determining depending on the accuracy of this. So basically, if you've got the ability to really strongly compress the input data coming in, then that can work great. But another problem worth paying attention to is you get this trade-off, right? Because if you have highly compressed representations of the data coming in, then sometimes it's very difficult to get your quantum neural network to be able to detect the patterns in that. So for example, one thing that I'll often do is I'll often suck up the cost of representing my quantum model or my data coming in unary rather than binary. That's exponentially worse in terms of storage. But it becomes mind-numbingly easy for the algorithm to be able to determine patterns in a unary number versus the much more structured binary number. So figuring out good ways of representing and encoding your data so you can trade off between like compression and the ease of the algorithm detecting patterns in the data is vital.
Shakir asks, do tensor networks help us in QML for big data?
Yeah, so basically, there's a couple of ways. If you take a look at the, first off, tensor network-based approaches often end up informing the kinds of structures for quantum neural networks that we end up picking. The example that I showed you near the beginning, with the Schold et al. Paper, that was taken from insight from Maris. So yeah, there's some insights that end up coming up from it, but I would say the biggest area isn't so much in quantum machine learning. These tensor network models have actually been revolutionary for areas in ordinary machine learning because they basically have been developed to give simple representations for complex data sets. So I really feel often tensor networks are some of the best and most natural competitors to quantum machine learning solutions inside the classical world. But there's potentially actually more insights that could be gotten by taking lessons from the tensor network community and applying it to quantum. But at the moment, I think it's been a bigger boon so far for classical ML than for quantum.
We'll finish off with, do you think adiabatic quantum computing will give us exponential speedup for NP-hard combinatorial problems?
Oh man, I'm very, very tempted to say exactly what I feel for this, but I'll edit myself because I've gotten wiser in my old age. No, it is strongly, strongly, strongly believed that the complexity class BQP does not contain NP. So we do not believe that AQC can give exponential speedups for these problems. The real question is whether AQC and quantum annealing can end up providing advantages versus existing SAT solvers in a scalable way. And the lessons so far have been that, at least on the D-Wave system, which, depending on what your definition of quantum is, may or may not be quantum, but it doesn't necessarily at the moment seem to be able to provide large advantages relative to highly optimized discrete optimization algorithms, in particular forms of like parallel tempering and other approaches like that. So no, I don't think that in general we're going to be able to solve NP hard problems using these types of approaches, but there's still a lot of discussion and debate about whether particular instances might be much more amenable to a quantum solution than a classical.
Thank you very much. I think we'll call it a session with this, because in 10 minutes, some of the summer school students have their own session for today. Thank you again, Nathan, for your time and the wonderful talk and the Q&A session. Thank you, everyone who participated in the talk, and hopefully we'll see you in some other session soon.
Yeah, thanks a lot. Really great being here. See y'all.
Okay.